So let us start with asynchronous type of counter today. But before that, we should understand what is synchronous counter and what is asynchronous counter. Okay, so if you consider asynchronous counter, then clock signal is applied to one flip-flop at a time. Okay, so at a time, one flip-flop is changing the state. And if you consider synchronous counter, then clock signal is applied simultaneously to all the flip-flops. Okay, so this is what is the basic difference between the asynchronous counter and synchronous counter. Okay, to asynchronous counter, the clock signal is applied to the single flip-flop. In case of synchronous counter, clock signal is applied simultaneously to all flip-flops. So in case of asynchronous counter, the clock is reaching to every flip-flop in a way just like ripple. So you know what is ripple. When we throw stone into water, then waves spread into the waters in circular fashion, and we call it as ripple. So one wave will create another wave will create the next wave, like this. So one flip-flop, when it is toggled, it is going to trigger the second flip-flop. Second flip-flop is going to trigger the third flip-flop. Third flip-flop is going to trigger the fourth flip-flop. So this is what is happening in case of asynchronous counter, and hence it is just like a ripple created when stone is thrown into the water, and therefore such type of flip-flops are called as ripple. Such type of counters are called as ripple counters. Okay, so asynchronous counters are ripple counters, and their speed is slow, and synchronous counters are counters in which the clock signal is applied simultaneously to all flip-flops, and speed of synchronous counter is greater as compared to asynchronous counters. Okay, so today we will be starting with asynchronous counter. Three-bit asynchronous counter. I will draw a logic diagram of this 3-bit asynchronous counter. So for 3-bit asynchronous counter, 3 JK flip-flops are used, and these 3 JK flip-flops, they are used in a toggle mode. And in order to use these flip-flops in toggle mode, you have to connect J input and K input of the flip-flop together and connect it to plus VCC or logic 1. Okay, so logic 1 is applied to J and K inputs of all the flip-flops. So whatever I have drawn now is a JK flip-flop which is used in a toggle mode. Okay, now let us call this as Q0, this as Q1, and this as Q2. Q0 bar, Q1 bar, and Q2 bar. So these are the outputs of each flip-flop. Now here you can see I'm applying clock pulse to flip-flop number 1. So we designate actually it as flip-flop number 0. So I am inputting clock pulse to this 0th flip-flop, and output of this 0th flip-flop is applied as a clock signal to the input of second JK flip-flop, which is flip-flop number 1 in our case. So this Q1 is applied as a clock signal to the next flip-flop, which is our third flip-flop. Okay, so These are the clock signals. Now here you can see Q0 is taken out, Q1 is taken out, and Q2 is taken out, and these form outputs of 3-bit counter. Okay, so this is 3-bit asynchronous up counter. Okay, so are you clear about this figure? So you always sit with your notebook and pen, draw figure along with me. While drawing, you will have practice and you will understand the concept behind the figure. Okay, so don't by heart the circuits, just remember the concept so that you can reconstruct it during your examination. Okay, so this is the diagram, logic diagram of 3-bit asynchronous counter. So here I am saying 3-bit counter. Okay, similarly we have 2-bit counter, we have 4-bit counter. Okay, now there is relation between number of bits and number of states that counter can count. For example, suppose if you consider a 2-bit counter, then 2 to the power of 2 is equal to 4. So this 2-bit counter is capable of counting 4 states. Now if you consider a 3-bit counter, then here you can observe 2 to the power of 3, which is equal to 8. That means your 3-bit counter is capable of counting 8 states. Obviously, for 4-bit counter, you have to calculate 2 raised to 4, which is equal to 16. So 4-bit counter is capable of counting 16 states. So if you go on increasing number of bits, the number of states, those can be counted. It goes on increasing. Okay, so here the relation between the number of states. Okay, so number of states is equal to 2 to the power of number of bits. So this is important. Write it down or take a screenshot because this is important for your examination point of view and basically for MCQ type of questions. Okay. Now let us see what the up counter is. Okay. So this is 3-bit asynchronous up counter. So what the up counter is? Up counter shows the direction of counting of the states. Okay. So if the direction of the counting of the states is in increasing order, okay, like 0, 1, 2, 3, 4, 5, 6, then that type of counter is called as up counter. In contrast to this, there is also a down counter, and this down counter is capable of counting states in decreasing order. For example, it will start with the maximum count, suppose say 7, and it will go towards 6, 5, 4, 3, 2, 1, 0, and again back to 7. So this type of counting is called as down counting, and the circuit which is performing such type of counting is called as a down counter. Okay, so are you clear about this? Type in the chat box because I cannot hear you. What happened today, I don't know, but I cannot hear you. So write in the chat box, is it okay? Shall we move forward for the working of the 3-bit asynchronous up counter, how it works? Write in the chat box. Shall we go ahead? Yes? Tejas? ओके, बोला काय तेजसला काही शंका आहे? तेजसला शंका आहे का तेजस? बर, ओके. So we'll go to the how the circuit works. Okay, so I will wipe out these things. In order to verify the working principle of this digital circuit, you have to assume the initial state. Okay, so let us assume that all flip-flops are in reset condition, because as this is a up counter, we will start from the first state and we'll assume that the counter is in the first state. So if counter is in the first step, then what will happen? Q0 will be equal to 0, Q1 will be equal to 0, and Q2 will also be equal to 0. Okay. Now, if these are the outputs of counter, so 0, 0, 0 will be outputted, as you can observe in this diagram. Now, let us see what happens if we apply a clock pulse to the first flip-flop. So here I am applying the first clock pulse to this flip-flop. Okay, so here we have shown level triggered, positive level triggered flip-flop. That means it is going to be triggered when logic 1 is applied at the clock pin. So here suppose I have applied logic 1 at the clock pin, then what will happen? So as clock is applied to this first flip-flop, the first flip-flop will toggle. Okay, so this first flip-flop will toggle, and it will change the state from 0 to 1. It will change the state from 0 to 1. But remaining flip-flops, as they have not applied with any clock pulse, the output of flip-flop number 2, it will remain as it is, and that of flip-flop number 3 will remain as it is. And what we are getting at the output of the counter is 0, 0, 1. So this Q0 is your least significant bit and Q2 is your most significant bit. So count that we are getting at the output of counter is 0, 0, 1 in this case for the first clock pulse. Okay. Now let us see what happens. Let us see what happens when clock signal is applied. Clock signal is applied. Second clock signal is applied. Okay. So when the second clock signal is applied, what will happen? That the first flip-flop will toggle and it will change the state from 1 to 0. It will change the state from 1 to 0, and as it is changing the state from 1 to 0, the flip-flop number 2 will be toggled, and it is going to change the state from 0 to 1. Okay, it is going to change the state from 0 to 1, and as this is 0 to 1 transition, the flip-flop number 3 will not change the state. So output that we are getting out of this is 0, 1, 0. 0, 1, 0 is nothing but 2. So initially we have got 0, 0, 0. Then we have got 0, 0, 1. And then we are getting 0, 1, 0. So this is our third count. Now, what happens here again is, you have to apply the third clock pulse. Okay. So what happens when you apply the third clock pulse? When you apply the third clock pulse, the first flip-flop will be toggled and it will be toggled from 0 to 1. it will be toggled from 0 to 1, and as it is making transition from 0 to 1, flip-flop 2 will not be changing its state, whereas flip-flop 3, as there is no change in output of flip-flop number 2, flip-flop 3 is also not changing the state. So state of flip-flop number 2 and flip-flop number 3, it will remain the same. So what you are getting at the output is 110. That means this is LSB and this is MSB. So 0, 1, 1. So 0, 1, 1 means this is a third count. Okay, are you getting the point? Tell me. Otherwise, I'm going to repeat it once again. Shall I repeat or shall I go ahead?
Yes.
Write in the chat box. Write in the chat box. Because whatever you are talking, I cannot hear. Write in the chat box. Atharva. You are saying something, write in the chat box. Shall I repeat this from initial count or shall I move ahead? Okay. I will repeat it once again. Once you understand this up counter, it will be easy for you to understand the down and bidirectional counter. Okay. So here we are going to use edge triggered flip-flop, negative edge triggered flip-flop, and for that reason I have drawn a bubble and edge here. Okay, so this is Q0 output, Q1 output, and Q2 output. Q0 output is LSB, Q2 output is MSB. Okay, so we are starting with the initial state, and our initial state is 0, 0, 0. So all flip-flops are in reset condition. So they have data 0, 0, 0. They have output data 0, 0, 0. This is your initial condition. Okay. Now, what we are doing is we are applying first clock pulse to the first flip-flop. So always we are going to apply clock pulse to first flip-flop only, because clock is directly applied to first flip-flop only. Okay. So output of a first flip-flop is given as a clock to second flip-flop. Output of second flip-flop is given as a clock to third flip-flop, like this. So this is our connection. Okay, now we are starting with state 0, 0 and 0. We are starting with the state 0, 0, 0. Now here I am applying the first clock pulse. So when I am applying the first clock pulse, as I am applying it to flip-flop number 1, what I can say is that this flip-flop number 1 will be changing the state. Okay, and as we are using JK flip-flop in toggle mode, its output state will toggle. That means it will be a complement of the previous state. So previous state is 0, it is going to toggle, means it will become 1. Okay, so when I apply clock pulse 1 to flip-flop number 1, the flip-flop number 1 will change the state from 0 to 1. So this change from 0 to 1 is applied as a clock to second flip-flop. Okay, but in order to change the state of the flip-flop, we have to apply transition 1 to 0 and not 0 to 1. Okay, so as here the transition is from 0 to 1, the flip-flop number 2 will not be activated. So its output will remain as it is, which is 0. Now output of this second flip-flop is applied as clock signal to third flip-flop. Now here you can observe at the output of second flip-flop, there is no change in the state. Output remains as it is. And as there is no change in the state, the clock will not be triggered. The third flip-flop will not be triggered. And hence, its state will not be changed. So it will remain 0 only. Okay. So now, after application of first clock pulse, you are getting the next state, and this next state is 0, 0, 1. You have to count in this order, starting from MSB to LSB. So it will be 0, 0, 1. So initially counter has counted 0, 0. Then it has counted 0, 0, 1. Okay. Now let us see what happens if outputs are like this 0, 0, 1, and we are applying a new clock pulse. And this new clock pulse in this case is our second clock pulse. So we are applying second clock pulse. Now here you can observe the previous state of flip-flop number 1 is at logic 1, and now we are applying trigger or clock pulse to this flip-flop number 1, and therefore output of the flip-flop will toggle, and initially as it is in state 1, now it will go to state 0. So output of flip-flop number 1 will change from 1 to 0. It will change from 1 to 0, and this output is applied as a clock to flip-flop number 2. Now here flip-flop number 2 is experiencing a transition from 1 to 0. So this is a negative edge of the clock pulse, and as this is negative edge triggered flip-flop, it is going to change the state, and it will change its state, and its previous state was 0, and it is going to toggle that it is going to change the state from 0 to 1. So now you can see the output of flip-flop number 2 is changing from 0 to 1. So this is a rising edge of the clock, and this is applied to flip-flop number 3. So as we are applying rising edge to flip-flop number 3, it will not be activated. It will not change the state. It will remain the same. So output of flip-flop number 3 will remain the same. Now we are getting the new state, and this new state will be, we have to read like this, 0, 1, 0. Okay, so the next state that we are getting is 0, 1, 0. Now assume this state and see what happens. We apply a clock pulse. Now your flip-flop is in state 0, 1, 0. And now I am applying here third clock pulse. And this third clock pulse is applied to flip-flop number 1. So as you can see, the flip-flop number 1 will toggle, and it will change its state from 0 to 1. Okay, so as it is making transition from 0 to 1, the flip-flop 2 will not be triggered, and its output will remain same, which is equal to 1. Now the output of flip-flop 2 is also not changing, and therefore the flip-flop 3 also will not be triggered, and its output will remain same. So the next count that we are getting here is like this. So we have to read from MSB to LSB. It will be 0, 1, 1. So next count our counter has counted is 0, 1, 1, which is decimal 3. Okay. Now your flip-flop is in third state, as you can see. So it is 1, 1, and 0. And again, suppose I am applying a fourth clock pulse to first flip-flop, and as I am applying clock pulse to first flip-flop always it is going to toggle, and its output will change from 1 to 0. And here you can observe the output of flip-flop number 1 is changing from 1 to 0. It is making transition from 1 to 0. Okay, it is a trailing edge of the clock, and therefore flip-flop number 2 will be triggered. And as flip-flop number 2 will be triggered, it is also going to change the state from 1 to 0. Okay, so now output of flip-flop number 2 is now making transition from 1 to 0. So which is negative edge of the clock and which is applied to third flip-flop. Now third flip-flop is toggled and it is going to change the state. It will change the state from 0 to 1 value. So output that you are getting at the output of counter is 1 0 0. So the fourth state that our flip-flop has counted is 1 0 0. Okay, so now considering this state, we are going to see what happens if we apply the clock pulse. So go on verifying each state. So here our initial state is 0 0 and 1, and now I'm going to apply the fifth clock pulse. As I'm applying fifth clock pulse here, the first flip-flop is going to change the state from 0 to 1. So as it is going to change the state from 0 to 1, flip-flop 2 will not be triggered. Its output will remain same, which is equal to 0. And as output of flip-flop 2 is not changing, the output of flip-flop 3, it will also not change. It will remain the same. It will also remain the same. So the state we are getting here is 1 0 1. So now our counter has counted the state 1 0 1. So it has counted the state 1 0 1. Okay. So here 1 2 3 4 5. Now we are going to apply the sixth clock pulse. Now our previous state in this case is 1 0 1 1 0 and 1. Okay, so I'm applying sixth clock pulse to the input of first flip-flop, and due to this, what happens? The first flip-flop will change state from 1 to 0. So it is making negative transition, and therefore flip-flop 2 will be triggered, and it is going to change its state from 0 to 1. And this change 0 to 1 is applied to third flip-flop. So it will not be activated because it is from 0 to 1, and therefore its output will remain the same. So what we are getting at the output of the counter is 1 1 0. So the our counter has counted the state 1 1 0. Now your initial count here is like this 1 1 0. And now let us see, we are going to apply seventh clock pulse, and as we are going to apply seventh clock pulse here, which is applied to first flip-flop, it is going to make a transition from 0 to 1. So this 0 to 1 transition is applied to flip-flop number 1. So as it is 0